This video will be covering some bug fixes that some people have encountered, and it will contain some paging optimizations. Let's get started. Some people have experienced this weird rainbow frame buffer effect that's been happening in QEMU when the RAM is set above a specific level. So we're going to implement some features to fix this. It's not happening on real hardware as far as I can tell, but we don't want this to be happening, so let's fix this real quick. So what I think is happening is the frame buffer is being overwritten by some section of memory that we've been allocating from the page frame allocator. So we just need to lock the frame buffer address. So to do that, just under the bit where we calculate the frame buffer base and the frame buffer size, we need to do a call to global allocator.lockpages. And then we need to give it a void pointer fb base, comma, fb size divided by 0x1000 plus 1. This needs to be 3 zeros, not 4. So this will lock the amount of pages that the frame buffer resides in. Now, the way that we've set the bitmap up is so that if we do this call, it will be outside of the physical memory. It could be outside of the physical memory rather, and that will cause a buffer overflow in the bitmap class. So we need to create some checks to make sure that that doesn't happen. So over now into bitmap.h, we can change this void set to a bool set, and in bitmap.cpp, we can change this void to a bool. Now in the bitmap subscript operator function that we have here, we can do if index is greater than size times 8, return false. So this is just checking if the index is within the bitmap size, preventing a buffer overflow. And same with in the set function, if index is greater than size times 8, return false. Otherwise, at the bottom we can return true. So the reason we're returning a bool here and here is so that we can tell if the bitmap has successfully set the bit or not. Now we're going to need that over in our page frame allocator. So in page frame allocator.cpp, we need to go down to free page and change this bitmap.set to if bitmap.set. Then we can change the amount of free memory and used memory. Now we're going to need to do that with free page, lock page, reserve page, and unreserved page. So we'll do that now. So if page bitmap.set, and then we can do this. If page bitmap.set, change the memory count, and if page bitmap.set, change the memory count. Alright, now we should be able to compile that and see if it still makes the weird rainbow pattern. So it's still creating the weird rainbow pattern, so the last thing we can do is clear the entire frame buffer to black as soon as the kernel has been initialized. And to do that, we'll jump over into kernel.cpp, and at the very start of the start function, we can do mem set boot info frame buffer base address 0 boot info frame buffer buffer size. And what this is going to do is change all of the pixels to black as soon as the kernel has initialized, which will get rid of that rainbow pattern. Actually, we should probably move this memset function at the bottom just after we move the new page map into the CR3 register. So we'll change the frame buffer colors to all 0 after we've moved the new page map address into the CR3 register. Now, as you can see, we no longer have that rainbow pattern, and we also have the added benefit of not having the UEFI print messages left over in the middle of the screen. The next thing I wanted to touch up, in paging.h, we are using Bitfields to define this page directory entry, but Bitfields are not consistent or reliable in the way that they are packed into a struct. So what I'm going to do is replace all of these Bitfields with a couple of getters and setters and some enum flags that we can use in place of these keywords here. So to get started, we can create an enum pt underscore flag, curly bracket, and a semicolon at the end. And we're basically just replacing these with enums. So present equals 0, comma, read write equals 1, comma, user super equals 2, write through equals 3, cache disabled equals 4, accessed equals 5, larger pages equals 7. Since we're not using a bit field, we don't need to put these ignored bits in anymore. We can just skip them with the enums. And with this 3 available bits, I'll create 3 enums called custom 0, which is 9, custom 1, which is 10, and custom 2, which is 11. And then finally, we have the NX bit, which is 63. Now this is the no execute bit, which is only supported on some systems, so only if supported. Right, now I also said in the previous video that the address is meant to only be 40 bits and not 52 bits, as the upper 12 bits are reserved or ignored, and the most significant bit is the no execute bit. So this is meant to be 40. But that's okay, because we're going to be replacing these bit fields with getters and setters anyway. So now that we've got these enums in place of these bit fields, we can just get rid of all of these members and replace it with a single 64-bit value called value. And that'll make sure the page directory entry struct is the same size as it was before. Now we can add our function members, so we need a void set flag, pt underscore flag flag, and a bool of what we want it to be set to. I'll call this enabled, and we need a bool get flag, pt flag flag. And this get flag member will just tell us if the flag is set or not. We need a void set address, uint64t address, and we need a uint64t get address. Alright, now we're going to have to create a new source file. We'll call it paging.cpp, where we can implement these new function members. Now before we leave, NX does not have a semicolon after it. So inside paging.cpp, we need to include paging.h. And the first one we're going to start is void page directory entry : set flag. We need the pt flag flag and bool enabled. Alright, now we need to create a bit selector. So uint64 bit selector equals cast to a uint64t1 bit shifted to the left by flag. And that's why we defined the enums the way that we did. So read write is 1, so it's bit shifted to the left by 1. Custom 1 is 10, so it's bit shifted to the left by 10. So that's why we've defined that like that. And now we can do value and equals not bit selector, which will set the bit to 0, and then if enabled, we need to set the bit back to 1. So value or equal bit selector. Alright, so there's our set flag function. Now we need the get flag function. So bool page directory entry get flag, pt flag flag, uint64t bit selector equals the same as what we have up here, so just copy that. And now we can return value and bit selector greater than 0, question mark true, else false. So if value bitwise and by bit selector, so we're choosing the bit, if it is greater than 0, which means it's on, it's enabled, we return true. Otherwise, we return false. Alright, now we need to do the get address function. So uint64 page directory entry : get address. And what we need to do is return bracket value and 0x 3 zeros, very important, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 Fs, and then 3 zeros. Bit shifted to the right by 12. So that will return the address. Now all these 10 Fs, each F is 4 bits, so that's 40 bits, which defines our address in the middle of the value. Bit shifted to the right so that we have the actual value. Alright, now void page directory entry : set address uint64t address. We need to bit mask address so that we only have 40 bits, so address and equals 0x 000000, and then we need 10 Fs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, Now we need to AND value with a specific bit mask to clear the address. So value AND equals 0xFFF, 3 Fs. Now we need 10 zeros, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. 3 more Fs. So that clears the address out of the middle of the value. Now we need to put the new address into the value. So value or equals bracket address bit shifted to the left by 12. Alright, so now we have all of our getters and setters for our paging struct. We need to actually replace the Bitfields in the page table manager with these new getters and setters. So we'll jump on over into page table manager, and we need to do if pde.getFlag pt_flag : present. And we can copy this bit here and just replace all of the references to pde.present. Now we need to change this pde.address equals to pde.setAddress. Get rid of this equals and surround this value here in brackets. So we're setting the address. So we'll do that with all of the addresses. So set address, get rid of the equals and surround this in brackets. Set address, get rid of the equals and surround it in brackets. And get rid of the equals, set address, and surround it in brackets. Alright, now we need to change .present to .setFlag pt_flag : present true. Copy this line here, replace this read write. So change present to read write. Now we can copy these two set flag lines and replace all of the references to pde.present and pde.readWrite. There's one more we need to do, and we need to replace this reference to pde.address to pde.getAddress brackets. And there's 3 of those we need to change. Alright, now we can compile and run that, and if everything went smoothly, nothing will break. As you can see, nothing has changed, which means it has been fixed successfully. Now, the next thing I wanted to do is clean up this kernel.cpp entry function because it's very, very messy. So what I'm going to do is create a header file and call it kernelUtil.h, which means kernel utility, and copy all of these includes, structs, and extern variables into kernelUtil.h. Then in kernel.cpp, all we need to do is include kernelUtil.h. Right. In kernelUtil.h, we need to make sure that we include pragma once, just in case we want to include it from anywhere else. Alright, that already looks a little bit cleaner. But we still have a lot of bloat in this function that I would like to get rid of. So what I'm going to do is create a function and a struct. We'll call this struct kernelInfo, and the struct will contain our page table manager pointer, page table manager. And now we need to create our function which returns an instance of kernelInfo, initialize kernel, and it needs to take a pointer to our boot info. Now in kernelUtil.cpp, which we now need to create, we can include kernelUtil.h and create the body of our initialize kernel function. So kernelInfo initialize kernel boot info pointer boot info. Alright, now this needs to return an instance of kernelInfo, so we need to create an instance of kernelInfo. So kernelInfo return kernelInfo. Right, next thing we need to do is create another void prepare memory and this needs to take a boot info pointer to our boot info struct. And this is the function that's going to prepare all of our memory, such as paging, etc., in the kernel initialize function. So we need to call prepare memory and give it our boot info pointer. And now what we can do is jump back into kernel.cpp, and from the definition of our memory map entries all the way down to this, just above this memset function, we can just cut that right out and paste it in prepare memory. Alright, so now this prepare memory function is doing all of our memory functions that we didn't want it to do before. But now in kernel.cpp we don't have a reference to page table manager, and that's why we have returned it in our kernel info struct. So inside prepare memory, we just need to move kernel info up above prepare memory. Inside prepare memory, we just need to set kernel info dot page table manager equals page table manager. Well, a reference to page table manager anyway. But right now we're declaring page table manager on the stack, so I don't want to do that. So we'll create a global instance of page table manager, and just remove this page table manager here. We need to initialize this page table manager globally as null, just to get rid of any errors that our compiler will give us. Alright, now back in kernel.cpp, what we need to do is do kernel info equals initialize kernel boot info. Now page table manager pointer page table manager equals kernel info dot page table manager, and change this dot to a pointer thing. Yep, and everything is working as intended. Now our kernel function is a lot neater. We can clearly see where we are initializing the kernel and where we are just playing around. Another thing we can do is move our memset into kernelUtil.cpp and place that just after prepare memory. And that cleans up kernel.cpp even more. As a matter of fact, we don't even need these map memory functions that we were playing with before, so we can get rid of those. And what we can do is new renderer.print kernel initialized successfully. And what this proves is just that our kernel has initialized successfully because our class is able to print to the Framebuffer, which it is very easily able to do. While we are here, and before I forget, we need to change this return to a while true. We can't return from this entry function here because that would cause our operating system to crash. So we just need a while true at the end to stop our operating system from crashing. There was one optimization I wanted to do before ending this video, and that's over in the page frame allocator.cpp. When we are requesting a page, we're searching through every single index every single time to try and find a page, but there is a simple optimization we can do to speed this up. That optimization is to store the index of the last requested page so that we can just start from there instead of starting from 0 all over again. So what we're going to do is create a UN64T page bitmap index equals 0. And then what we can do is replace this index here with page bitmap index and this index here with page bitmap index, and get rid of this UN64T index equals 0. We need to keep this semicolon here just to make this for loop still work. Then we can replace this index, and this index. Alright, now every time we go through a request page, we will be starting from the page bitmap index, which will save a lot of iterations through this loop. That has caused a problem, however, and that problem is that when we free a page, that freed page will now be before this page bitmap index. So if we free a page and the new index is less than the page bitmap index, then we need to set the page bitmap index to the new index. Alright, so if page bitmap.set false is successful, then we need to if page bitmap index is greater than index, page bitmap index equals index. Alright, we need to copy this little line here and put it in every single function that frees a page. So that's free page and unreserved page. So that's a little optimization we can do to greatly speed up the time it takes to request a page. We can do a little test and allocate 2000 pages with and without the optimized code to see how quickly it can do that. So I'll just undo everything that we just did, go into kernel.cpp and do a for int t equals 0, t less than 2000, t plus plus, and we can do global allocator dot request page. Then afterwards we can do new renderer dot print done. So we're going to request 2000 pages and then print done. We'll see how long this takes. Actually, we'll make it 5000 pages just to increase the amount of time. So we'll see how long this takes using the unoptimized version. Here we go. So that took about a second and a half. Now we can go back into PageFrame Allocator and redo all of that stuff that we just undid. Now we can compile and run that again and see how quickly it does it. Now, as you can see, it was pretty much instantaneous. So that's a massive improvement on the page requesting speed from such a simple optimization. There is even more optimizations that we can do, but for now, this optimization will do just fine. We'll get rid of this because we don't need that anymore. And that will be it for this video. Thank you for watching, and I will see you next time.